Okay, hi everyone. Today we're going to solve another problem, that is LeetCode 1061 lexicographically smallest equivalent string. It's a medium level problem and it's a very good problem. So let's say you are given two strings of the same just a second. Okay. So we are given two strings of the same length, that is s1 and s2, and a string base str, that is base string. We say s1 of I and s2 of I are equivalent character. For example, every ith character from s1 and s2 are mapped to each other and they are said to be equivalent. For example, if s1 is ABC and s2 is CDE, we have A that is mapped to C, B is mapped to D, and C is mapped to E, and they are called equivalent characters. That is, A is equivalent of C, B is equivalent of D, and C is equivalent of E. Now, equivalent character follow the usual rules of any equivalence relationship. So these are some set relationships, that is reflexivity, that is if A is equal to A, then A is equal to A, and symmetry, if A is equivalent of to B, then it is also true that B is equivalent of A, and transitivity, that is if A is equivalent of B and B is equivalent of C, then A is also equivalent of C, this case. So for example, we are given the equivalency information from S1, that is equal to ABC, and S2 is CDE. Now ACD and AAB, okay, are equivalent strings of a base string, that is EED, and AAB is the lexicographically smallest equivalent string of base string. Okay, this line could be confusing, this example, so let's understand this by this test case. So we have S1 string, that is Parker. So S1 string is P A R K E R, Parker, and S2 string is equal to Morris, Morris. Okay, and their indexes are 0, 1, 2, 3, 4, 5, 1, 2, sorry, 0, 1, 2, 3, 4, 5. Fine. And we are also given a base string, and base string is parser, which means let's it be base str is equal to PARSER. Yes, now base string is parser and their indexes are 0, 1, 2, 3, 4, 5. Okay, so this question says that P is now, let's take this by examples. So first case, for first, which means the first case, which means zeroth index, the first element, that is P is now equivalent to M, right? And we need to make it in such a way that everything that is equivalent to each other will form some type of relationship. For example, if P is equivalent to M and we have P here, then we need to have for P the smallest element that is equivalent to P. Now we have P and M, this is only one relationship, and in this case P and M, which character is the smallest? Lexicographically is smallest, it's M, right? Which means if P has these associativity, if P is related to M, equivalent to M, or some other characters or some other characters, then the smallest out of them is M. So that should be chosen, and this is going to be, so at this base string, when we are returning the answer, the conversion of this base string is going to be M. At P place, I'm going to write M here. Now, and I think you can now understand by this diagram that this is more like a set problem where you have P, and where you have P and M, there is a relationship between them, but M is associated with P in this way. So M is basically parent of P. And when we are dealing with parent of each other and including the sets in a graph system, then it's a union find or disjoint set union problem. So if this is a case, then we can construct a set side by side. So if P is equal to M, then the smallest element is M. And when the set is created for P and M, this will be like this: M is the leader, Why m is the leader? Because m is the smallest character out of these two in lexicographically terms, and p is the child of m because p is lexicographically greater. And let's consider another element. So second element is a and o. So a and o are equivalent. A is smallest, so for this case I will, you know what, let's consume little, let's less space. Yes, so for this character m is smallest, so I will say m and child is p. So second case I will say a equivalent to o. A is smallest, so I will say a and the child is o. For third case we have r and r equivalent to r is smallest, but it doesn't matter, so r will be just sitting there as a one set because r child r doesn't make any sense, it's one and same thing. And then we have, because in the default implementation of a union find parent linear data structure, we initialized every character with its parent, and the parent is by default is the character by itself. So we don't need to make a relation that r is a r because this is already declared in a default implementation of union find. Now for the fourth, that is the third index, k and r. So this is interesting, k and r, which one is smaller? K is smaller, so I will say k is now, k is the leader and r is the child. K is the parent and r is the child, this case, right? So r was a unique set initially, but now they are merged. Fine. Now we have another thing, that is fifth element is e and I. E is equivalent to I. Which one is smaller? E is smaller, so I will say E is leader and I is the child. And then we have sixth case, that is R and S. R equivalent to S. Now R is smaller, but this is interesting. So R child should be S. This is like true, but our parent is K, right? So this is a path compression technique where we can reduce this path and directly connect it with S. And why are we doing it? Because see, if I will say that for S, which is the least lexicographically element that is associated with S, then I will say R, but R is connected to other element that is K, so I will return K for the R for the S as well. So for S, the least lexicographically is K, and this is where we are going to path compress it and connected with, like, connected it like this, that with K we are connecting it R and S. Fine. So when we have created this type of these sets, these are basically sets in disjoint set union. Now we are going to parse it. For P, what is the parent of P? Look for the P here. P is there, so P parent is M. A, what is the parent of A? There is no parent of A, so we will consider it as it is, that is A. For R, what is the parent of R? For R, this is the child and this is the parent, that is K. For S, what is the parent? K. For E, what is the parent? There is no parent, so we will type it as it is. And then we have R, what is the parent of R? Is K. So this is the answer and this is same as the answer. Now if you want to try these test cases, you can obviously dry run them on this algorithm, but I won't be doing it just to make the video more crisp and clear, and I will be straight jumping on to the yeah, I should be straight jumping on to my implementation. Now the first thing, we need to have a union find data structure, so I will be creating a class of it, or an object, well, class basically, and then I'll be creating an object in the in this function. So union find class, and everything will be public because we are going to access the parents later on. Now we have a vector of character and this is parent. It's not initialized with anything because C++ will give you an error that you cannot initialize anything in the class, because class will allocate memory, because memory is only allocated when an object is created of that class. and when that object is not created, by initializing this parent vector will create some type of ambiguity that memory shouldn't be created when a class is initialized, but it is created in this case, so we cannot initialize it. But for the same purpose, I'll be having a constructor, and this is a union find default constructor with no parameters. So first I will be resizing the parent by 26 elements. Now for loop I is equal to 0, I is less than 26, which means this loop will be running for 26 times, that is the alphabets in a that are 26 alphabets, and I will be doing what I, so parent of I is equal to character value of I plus of a, and by this how we are going to have a vector of so for example, at 0th index we are going to have a, at first index we're going to have b, c, d, e, and so on. The whole alphabets will be stored into the parent vector and initialized with, so a is parent of a is a, parent of c is c, and so on. So this is the constructor, and now we can make our main function, that is find parent, and find parent will take one argument, that is a character. Now if the parent of c is equal to c, sorry, c minus of a, if parent of c minus of a is equal to c, then it's a different thing. We are just going to return c, that we have find the element that we are looking for. Otherwise I will say that parent of c minus of a, if it is not equal to uh, if it is not equal to the character itself, then we will keep on. So this is a path compression technique where we are compressing the path. So then I will say that find parent of the one that I have just got, fine. And now we have another function, that is merge. It will take two, it will take two arguments, that is a and character b. Now we need to find the parent of a, and that is equal to find parent of a. Similarly we need parent of b. After having these parents, because it's a path compression technique, we are not relying on the size or rank or anything, so we can just simply make our execution that parent of a. So if parent of a is lexicographically smaller than parent of b, then it means the parent of a should be the new representative or leader or new parent, which means that parent of b, now b character, the parent of the character b is now connected to parent a, and for that we can say that parent of b minus of a, that to get the index, is equal to parent of a. And else if there's any other condition, that is if they are equal, or if they are equal or they are not even equal, and parent of b is smaller, then we will say parent of a minus a, which means parent of a should now be connected to parent of b. Fine. Now after this we are done with our implementation for union find data structure. Now we can just initialize the object, and that is union find uf, and we also need int n, that is equal to s1 dot size, and we also need a string that we need to return. Actually we don't need a string, we can work with the base string only. Yeah, yes. So what I will do is, now we are going to merge all of them, right? Because s1 character, that is s1 ith character, should now be merged with s2 ith character. So I will be start I is equal to 0, int I is equal to 0, I is less than n, I plus plus, and union find dot merge s1 of I and s2 of I. After merging them, I'll be iterating over the base string, and I will say base str of I is equal to find parent of the character that is provided by the base string, and finally return base string. So let's see if this will work. Okay, find parent is a uf dot find parent. It does work on these test cases. Let's see if this will be accepted. Okay, it is accepted and it is also performing pretty well. So yeah, this is the problem, and I have solved this with the help of union find algorithm. uh, it also has a string tag, which means it can be solved with string. Maybe, like, yeah, I mean, you can also use a hash map or a linear data structure just parent, but the ultimate concept will be to roll over the um, smallest lexicographical parent, and that concept is well supported by union find data structure. You can also do it in your own row implementation by not using, well, technically you will be using a union find concept, but you won't be using the standard union find data structure. So yeah, I think this is the best way to solve it. And if you have any other ways, if you have doubts related to this code, or if you want to copy the source code, then it is provided in the description. If you want to check out the solution for this problem on LeetCode, I have also posted the solution, so you can also check that out. And yeah, that's it. Thanks for watching and have a good day.